Hey everyone, welcome to Quantum Photonics. Hi Bees, how are you?
Hey, Sarah.
Hey
Doing
Jim,
well.
how are you?
Good evening.
Hi, Jim.
Good evening.
Hey Jim, welcome. Yeah, thanks so much for joining us as an honor guest speaker today. We're so excited to have you. And also at the stage, we have Cecile and Abby's here. And welcome everyone in the room.
Thank you. Yeah, I'm looking forward to talking about one of my favorite topics, looking for life beyond Earth.
Yeah, me too. I'm sure everyone here are so excited to learn from you, especially the looking for the life beyond Earth is one of the huge mission of the NASA, and we all know you contribute a lot to NASA's. So would like to learn from you today, and very honored to have you here to talk about this very exciting topic.
Yes, welcome, Jim. I've been, learning from you and your sharing, down in the audience in your astro rooms so much, and I really appreciate for the wonderful content you shared with us. Yeah, looking forward to the your session with quantum photonics.
Well, thank you very much. That was so kind of you to say. I really enjoy talking about what we're doing, letting people know what's happening and what we're finding and what we need to yet do.
Yeah, thanks everyone. Thanks for being here. We have JimGreen today, honored to join us as a guest speaker. So we will start the session very soon. Please feel free to share our room today or pin some friends you feel may be interested to this topic. So feel free to engage the conversation later with us. So Jim is very honored to take the time with us with his busy schedule. So we will cherish his time, and we only have 1 hour today. So feel free to join the discussion if you would like to ask anything when we open the floor. So we are waiting. So today's format will be so Jim will give us a quick introduction or overview about this fascinating topic on how to look for life on exoplanets, and then we can take some questions and to see how the conversation will go with the flow. Okay, that's awesome. Maybe I can do a quick introduction about James' background. So I pinned the link of James' short bio. So we all know like Jim is well known as a very yes as a very famous scientist and physicist in NASA. Especially, he worked as a chief scientist for a few years for NASA. And I see Jim did lots of great contributions. And also, Jim drove lots of effort to help NASA to development the mission on how to look for life on exoplanets. So we are very honored to invite Jim here today. So I will pass the mic to Jim. Welcome to Quantum Photonics.
Well, thank you so very much. Let me start out by setting the stage. When I got my undergraduate degree in astronomy, it was optical astronomy. We used telescopes, ground-based telescopes. I used a 12-inch Alvin Clark refractor when I was in high school, and much bigger ones. at University of Iowa. And we were measuring all kinds of stuff, from stars to galaxies, etc. There was some talk about the possibility of observing planets around stars, but that was largely dismissed. So this is in the 70s and 80s that we just figured that we're never going to see a planet around another star beyond our solar system. Well, in the 90s, we were proven wrong. What was happening is there were a variety of techniques that were coming out that really enabled us to start the process of finding planets. This was at first very difficult to prove. It required a couple methods, and those methods needed to indicate that something about the planet, like its size and how far away it is from the star, and whether that fit the model that we have here on our own solar system. So our solar system has 8 planets. It has 2 huge belts of debris. One's called the asteroid belt that sits between Mars and Jupiter. Another one is called the Kuiper belt, which sits beyond Pluto, which sits beyond Neptune, for which Pluto is the largest member of the Kuiper belt, and at one time, of course, thought to be a planet. But it is a very large object and what we would call a dwarf planet. So we used our own solar system as sort of a yardstick. And so when we were finding planets around unusual stars, like a pulsar, that was the first planet we saw was around a pulsar, it was really hard to imagine. But soon, in the 90s, many different types of telescopes were making a variety of measurements, and the best technique that finds the most planets is called the transit technique. This is where you take a telescope, you stare at a star, and you make the same measurement over and over again. You measure the light coming from the star. And if the light dims for a period of time and then reestablishes its brightness as it was before the dimming, then you can think of something moving in front of you and the star. That's called the transit technique. Now, we have scientifically known about the transit technique for hundreds and hundreds of years because Venus and Mercury move in front of the sun, and we see these transits. So the concept of the transit is well known, and in fact, a transit of Venus in the 1800s was used to determine if it had an atmosphere or not. You know, we see all our planets, but we did not know they had atmospheres. We knew Earth had an atmosphere, but we didn't know they had atmospheres until we really, terrestrial planets, until we really could see and tease out Venus's atmosphere as it transited the sun. The sunlight went right through the atmosphere, and there was a bright ring around the planet. And indeed, it just illuminates the atmosphere and modifies the sunlight. And so that's a huge step forward. So this transiting technique then was developed really well in a couple spacecraft, and probably the best well-known spacecraft that used this technique to find exoplanets is Kepler. Kepler was launched 2009 when I was at NASA headquarters. It was selected in the Planetary Science Division that I was the head of as a discovery mission. And because of the intense interest by the astronomy community, we transferred this mission from planetary to astronomy. And so the Astrophysics Division at NASA headquarters actually implemented the mission. Now, the purpose of the mission was to stare at a particular region in the sky look at all the stars that it could see in that region, and just sit there and measure the intensity of the light and look for these little dips. And it did that, and it looked at about 120 or maybe even 130,000 stars all at once. Just an enormous step forward in our ability to make these kind of measurements. And indeed, it started to see many of these stars with dips in their light as it was measuring the intensity of the light every 30 seconds. And so consequently, we build up this huge database, and right now, Kepler has discovered 4,000 planets. Now, Kepler was we actually had to turn it off in 2018. It lost its ability to point and track and look for planets, and so it really found just an enormous number of exoplanets. And a couple things came from that were pretty exciting. First thing you want to know is, well, are those planets like our planets? In other words, are there terrestrial planets ranging from the size of Mercury up to the size of Earth? That's what we have in our solar system. In other words, Mercury is our smallest terrestrial planet. The next smallest is Mars, and then Venus, and then Earth in size. What about gas giants? We have several gas giants. We have two, actually. In the outer part of our solar system, we have Jupiter and Saturn. And then we have two what we call ice giants. Even though they're gas-filled, their composition is very different than Jupiter and Saturn. Jupiter and Saturn has a lot of hydrogen and helium, whereas the ice giants actually have a lot of ammonia and water and other elements in addition to hydrogen and helium. And so we distinguish those. Those are also smaller than the big Jupiter and Saturn. So that's our set of planets, and we can see from the Kepler data, and we can categorize all the planets that we're finding into categories. And lo and behold, we find that Kepler also observes planets we don't have analogs for in our own solar system. There's a particular terrestrial planet, in other words, one that's Earth soils, maybe oceans and atmospheres too. There's a particular type of planet that's bigger than the Earth. So Earth is not the big end member, so to speak, of terrestrial planets. It's really another one. It's called a super Earth, and it may have as much as 10 times the mass of the Earth. All right, and now that doesn't mean it's 10 times as big, because rock really crunches down. It might be 1.5 or maybe 2 times the size of the Earth, but no bigger than that. And these planets we don't have in our solar system, and they are called super Earths. We do see a lot of Neptune-sized planets. We do see a smaller number of Jupiter-sized planets. And so there's quite a distribution of planets that we've been finding around these stars. That's fantastic. Now we know planets exist. Now we know there are other worlds that orbit stars. Now we know that when stars form, planets could form also. But then another startling fact came out of the Kepler data that's really unbelievable in many ways, and it's really changed our thinking. And that is, based on what we saw in this set of stars, how many planets we found, the types of planets we did, we can statistically determine how many planets are in our galaxy. Okay? It's done with mathematics, it's done with statistics. And the end result is there are more planets than there are stars in our Milky Way. That's fantastic. That's an absolutely fantastic result when you think about it. And in fact, that means planets are everywhere. They're not just as we thought maybe early on in the 90s when we started to see some planets that we'd find a few of them. They're everywhere. And in fact, there's even some indication that there are planets that have been thrown out of solar systems. That's a fantastic idea. What happens to interactions between planets that end up taking a planet in our solar system, a solar system around another star, and throwing it out of our solar system? How does that happen? And in fact, we're looking for a planet right now in our own, that orbits our sun, that we call Planet X. Others call it Planet 9. It's a Neptune-sized planet, and it may be at a huge distance away, maybe anywhere from 600 to 900 times the distance between the sun and the Earth. We call that an astronomical unit. So this planet 9 may be between 600 and 900 astronomical units, a planet that was nearly thrown out of our own solar system. And there's plenty of good reason to believe that that indeed happened. So since the 90s, an enormous amount of change has been made in these concepts. Now, the next big concept, of course, is now that we know they're out there, let's figure out if they're habitable. In other words, let's find out if any of these planets could harbor life. So there are a couple of ways that have been determined how to do that. But the first thought is one of, let's go to our solar system and look at it, study it, and then figure out why Earth is so special. And Earth is very special because right now it is a certain distance away from the sun. If it was closer, it would be hotter. If it was further, it would be colder. We are at a perfect place from the sun where water exists on this planet in three phases. It exists in liquid, vapor, and solid form, okay? And so we call this area around a star where the light from that star can actually bathe the planet, keeping it in this great condition to have water. We call that area the habitable zone. So the habitable zone idea started out as a very theoretical idea, but is really proven to be a good construct to then separate in the set of planets that we see what ones are at the right distance from the star and what ones are either too close to the star or too far away from the star. And now we have a set of planets that we can look at in greater detail. So it's enabled us to really refine our search. So the concept of the habitable zone has been talked about a lot. We also know by looking at the evolution of Venus, Earth, and Mars that there's a wild card in whether a planet can be habitable or not. You could be not be in the habitable zone, in other words, be in a region where it's too cold, or be in a region where it's too hot, and still be habitable. And that's because of the unknowns of the atmosphere. In fact, when we run our simulations about Venus, it turns out Venus was a water world. It was a blue planet just like the Earth. And in fact, it had a wonderful cloud structure in the very front of it that reflected light, that kept it cool and enabled water to stay on its surface, both in liquid form and vapor, but probably even ice form, because Venus spins very slowly, so the night side can get cold. Well, what happened, of course, is we now know that the atmosphere couldn't keep the major sunlight away long enough that finally Venus, and it could be also due to a lot of volcanic activity, changing the constituents of the atmosphere, turned out to be dominated by carbon dioxide, which we now know because we studied Venus in the 70s and 80s, is going through a runaway greenhouse effect. So Venus is no longer habitable. The surface is hot enough to melt lead, and the atmospheric pressure is enormous. It'd crush a car like a pancake if it sat on the surface. So Venus is not habitable anymore, but it was at one time. So this is really exciting. We can broaden our idea about a habitable zone if we have information about an atmosphere. And that would mean you have to have an understanding of what's in the atmosphere and how much is in the atmosphere, because that makes all the difference in the world. Now, we are modifying our atmosphere. Life modifies the Earth's atmosphere and has in its history. And now atmospheres, it has a huge amount of oxygen, where in the past it didn't have a huge amount of oxygen. And so life has actually changed a lot of the carbon dioxide that was in our atmosphere and converted it into oxygen. And that's one of the things that life does. So that's what we call then signature. So a biosignature, if we start looking at atmospheres, can tell us about whether a planet may have the ability to harbor life or not. Now there are a bunch of biosignatures, what we call biomolecules, molecules that life life modifies, and they end up in the atmosphere as trace gases. One trace gas, in other words, a trace means there's a hint of it. If you grab a bunch of atmosphere and it's in it, you'll find it in there, but not a lot of it. One trace gas is methane. All life on Earth, cellular life on Earth, generates methane. So methane is a wonderful biosignature. Unfortunately, there are all processes, chemical processes, that can generate biotically. And as you get under the crust of the Earth, we see along with water that has seeped down through our ocean into our crust, along with certain minerals like olivine, a chemical reaction occurs and methane can be generated, and then the methane seeps through the crust and enters the atmosphere. So 95% of the methane in our atmosphere is generated by life, and a few percent is not generated by life, but it's abiotic. So just because we see methane, we can't say for sure there's life. But that's really important. So we put those things off to the side. These are the things that we want to look for. So the key is, let's find these planets, and then let's go after their atmospheres, and then let's see what's in them, and then let's find out if there are biomolecules in it and how much, and get an idea of whether life could be part of the biosphere of those planets. So where are we in this quest? Well, we're pretty far along. As on 4,000 planets. After Kepler died, we had a new spacecraft. It's called TESS, which is a transiting explorer satellite. And TESS has been observing now for several years and has found several thousand what we call candidate planets. Once again, once we see the dip in the light, we have to go back with other methods and verify that that is consistent with a planet with a certain orbital period. And indeed, if you can do that, then we put it over in the planet column. And so just 2 weeks ago, we exceeded the 5,000 exoplanet mark, even though there's another 3 or 4, maybe 5,000 more planets that need to be verified. So we're well on the way of seeing all kinds of planets all over the place. Now, Kepler and TESS are great because they find these planets, but that doesn't tell us much beyond the size of the planet, how far away it is from the star. In other words, what's its orbit, and whether then it's in the habitable zone or not. Now, that's all important. It's really critical, narrows the search for life on that segment of those planets, and allows us to go after them. So the next big step is looking at the atmospheres of these planets, okay? So this is just, to me, unbelievable, because, you know, when I was an undergraduate in astronomy, we didn't even think we could see a planet, and now we're going to look for its atmosphere. I don't know if you've seen any of these beautiful shots from space station. They're coming out of the night, and they're just coming into the day, and off in the distance you can see the horizon, and there's just this little blue line that hugs the horizon, and that's the atmosphere of the Earth, okay? And that's what we're going to find and look at and interrogate on an exoplanet. I mean, that's just believable, but that's the step that we're doing. And what's going to make those measurements? It turns out that spacecraft is at the right place. It's being commissioned right now, and it is called the James Webb Space Telescope. Now, this is a huge telescope. I mean, it has 9 times the collecting area of the Hubble Space Telescope. I mean, it's just phenomenally large. And we launched it on Christmas Day. We got it to a place where it's behind the Earth, so it doesn't see the Earth except at night, although it's not designed to look at the Earth. It's designed to look away from the Earth, and therefore away from the sun. And that's why it's got this heat shield. It's got this big heat shield that points to the Earth and points to the sun with the telescope on the other side. And we want it there because the range, in other words, the type of light that this telescope sees, is called infrared. So if you go, go at a campfire, close your eyes, hold your hands out, and point to the fire, you're feeling the heat. You're feeling the infrared radiation. You're feeling the light that is generated in the fire, landing on your hand, stimulating your skin, and you're sensing the heat from it. And that's what Webb will do. It is designed to look for the faintest signature. Let me give you an idea. Webb could see the heat on a bumblebee if it was on the moon and Webb was on Earth. That's phenomenal. And the only way it can do that, because there's so much light from our sun, so much reflected light from our Earth, is to keep it cold. To sense the heat, you have to be colder than that, than the heat you're sensing. And so that's also why Webb is in a position where it's isolated and all the instruments are really cool, getting really cold. How cold? Well, like 350 or 400 degrees Fahrenheit minus, in other words, below zero. Now, we have another scale we call Kelvin, which is the coldest thing in the universe is 0 degrees Kelvin. You can't get colder than 0 degrees Kelvin. And just today, this morning, we got one of the instruments at 7 Kelvin, okay? So that means we are now in a range where this instrument can operate. Now, we got several other instruments that need to get colder, and so we're still several weeks away, but when we get the instruments to be that cold, what will happen next is now we'll go after the atmospheres. So we're on the precipice of a revolution in observing exoplanets using a fabulous telescope. It took us a long time to build it. And when I was at NASA headquarters, I was very much a part of what we wanted the telescope to do. And I'm very happy to, feel very proud to be part of that. And now it's getting near its operation. So how is it going to observe atmospheres? Well, it's going to observe atmospheres just like we observed the atmosphere of Venus for the very first time. We're going to use the same idea. So as the planet starts transiting the star, we're staring at the planet with this huge telescope. We're going to see how the planet's atmosphere modifies the spectrum of the star, okay? And if it doesn't modify the spectrum, then it doesn't have an atmosphere. Then it's more Mercury-like, all right? If it does, then what's the modification? You know, can we determine if there's water there, if there's carbon dioxide, if there's methane? And so that's one of the really critical techniques. Another critical technique is looking for emission from the atmosphere. So if you shine light on our atmosphere modifies the solar spectrum, but it grabs that light, holds it for a little while, and then emits it, re-emits it in a different direction. And that emission, it can be observed when the planet is on the other side of the sun before it goes into eclipse. So when we look at a star, we're going to be looking for not only the times when certain planets are transiting, but when certain planets are passing behind the star just before it goes into eclipse. And we're going to be looking at the emission from the atmosphere. Now, that's going to be really hard to do, but we're set to do that. And that's phenomenal. Here, we have a series of proposals that have been accepted. And so Webb has a whole year plan already. There's, we know exactly what it's going to do, and after that, and after that, and after that, and after that. And we're just going to line up all this stuff that it's supposed to do and start going through it. And what will happen is it's not all exoplanets. It'll be looking at some of the oldest galaxies ever made in our universe. That's really one of the top things it's designed to do, is to look back in time and see, after the first stars came together, how they came together to create a galaxy. All right? So we're going to be looking at the first galaxies. And that's going to be tremendously exciting. And so not only do we see exoplanets and whether they're in the habitable zone, and then whether they have atmospheres, and then the idea would be, would they have life, and could life be supported in those atmospheres? Webb is really doing many other astrophysics things. So the key is, how many exoplanets are we going to observe by JWST this year? This first year of observation. And there's about 63 exoplanets we'll look at. Now, these exoplanets were carefully selected. And they're carefully selected for their size, their type, and being in the habitable zone or being on the edge of the habitable zone. They have unique characteristics that we believe Webb will be able to make some really astounding measurements and progress. And so we're set to do that. Now I'm going to end by talking about one particular planetary system. It was actually found by Spitzer in 2016, and the star is called TRAPPIST-1. It's in Aquarius, the constellation Aquarius, that TRAPPIST-1 system has 7 terrestrial planets. 7 terrestrial planets. Now, this is a fantastic system. When you look at ours, we have 4 terrestrial planets. We have, of course, Mercury, Venus, Earth, and Mars. Those are the four. And the TRAPPIST planets are either Mars size or they're Earth size. It's just a phenomenal set of planets to look at. And it turns out of the 7, I would say 4 of them are either directly in the habitable zone or in the edges of the habitable zone. And once again, that's a good place too. We want to look and see how if they've got atmospheres, whether they're hanging on and really providing still an environment for life. Earth is right in the middle of the habitable zone right now, and Venus is too hot; it's outside of it. Mars is just on the outer edge, and it's cold and arid. But it also, early on in its life, was a habitable planet, but lost its water. It lost its ocean and lost most of its atmosphere. So when we look at these TRAPPIST-1 planets, and right now they're not. TRAPPIST-1 is the name of the star, and each of these planets then have a certain designation, and they're designated B, C, D, E, and F, and H. Those are the letters associated with a planet. And planet E is just not only a little smaller than the Earth, but it's sitting right nice in the habitable zone. Now we're going to look at these, all of them in transit, but we'll look at several of them in particular in eclipse. The eclipse technique, looking at the atmosphere, in particular if they have atmosphere, and really tease them out. So the TRAPPIST system is just phenomenal, and I think we're really due for some spectacular discoveries. So have we found life beyond Earth? No, not yet. But life on exoplanets must be out there. That's my personal opinion. And we're methodically stepping towards making spectacular discoveries that will lead us to an understanding of what it takes to harbor life on a planet orbiting another star. Thank you very much.
Wow, thanks, Jim. Very interesting topic, and thanks for your speech. I got a big overview about how we start to search for the life on the exoplanet, and also thanks for sharing how you started this journey for your career. So I know lots of people must have some questions, so we will go to the PTR order. Yeah, I have very lots of questions at my hand, but the first question, if I would ask, that would be, looking for life. How do you define we have found life? What's the parameter for life? Can we easily say we found life just because we found oxygen? Thank you.
Very good question, because many people are confused by these biosignatures. All biosignatures that we know of can be generated by non-life processes. So that makes it really difficult to argue scientifically that if we see like methane or oxygen, that it has to be life that's doing it. So I wrote a paper that's now gotten to be well known. It's in Nature. It's Nature Communications, and it's about developing a scale that gives us confidence that we're moving towards a detection of life. And it starts out that the scale goes from a confidence level of 1 to 7, where 7 is confirming that we have life, and 1 is the start of our first observation, where we have some indication of, let's say, a biosignature. Now, this scale is called the cold scale. It's called the confidence of life detection, or COLD. And so, as you see, we have posted. Thank you, Aaron, for posting this this scale, this article in Nature. And it really starts out by making the initial observation and saying, okay, we think we see a biosignature. Now that starts out with a cold scale of 1, but to make it 2, you have to eliminate all aspects of instrumentation. You have to really repeat the experiment and really see it. It has to be well above what we call the background of an instrument. It can't be just a fluke that things worked out and you saw it once and you now can't see it again. It's got to be reproducible. So that you then start getting into the second, that'd be confidence of life detection number 2, cold scale 2. And so indeed, to work up that scale, you now need other biosignatures. Can we see several biosignatures together, like oxygen and methane and CO2? Plant life uses CO2. And so you then have a collection for which it makes sense. You also have to look around and see where you see this. Do you also see water vapor? If you don't see water vapor and there's no liquid anywhere, then our astrobiologists are of the mindset that you're not looking at a place where life could exist. And here's the reason why. It has to do with the definition of life. Life has 3 attributes. It metabolizes, reproduces, and evolves. That's it. If we can find a system that does that, we're going to call it life, okay? So we have synthesized this down to the simplest terms. And so when you look at those 3 things, we're not going to be able to observe reproduction. We're not going to be able to observe evolution. But what about the metabolic process? Well, the metabolic process is really all about extracting energy. And for life here on Earth, we take in water, which is a liquid, of course. We then consume. The water is used as a solvent. We extract energy out of that. The waste, the water then is used to eliminate the waste. And that process is the metabolic process. The metabolic process. So we firmly believe, astrobiologists, that we have to have liquid for a metabolic process. Now, that doesn't mean it has to be water. It could be other types of liquid. Like on Titan, Titan is the only other body in the solar system that has liquid on its surface. It's a moon of Saturn, but it's not water. It's liquid methane. Okay, it's so cold there that methane as a gas is now turned into a liquid. It's literally raining methane right now in the southern hemisphere of Titan. It's a fabulous body, and in our solar system. I'm sure we're looking at exoplanets that are like Titan, and we don't know it yet, but we're going to find them. And so another way to get up the cold scale is also recognize that the theories of life in terms of the environment and what it requires process is also in the layer that you're looking with these other biosignatures. And so the confidence of life detection is critical. Now that means, okay, I'm not going to be able to come on Clubhouse in 6 months after we look at TRAPPIST and say, we found life on TRAPPIST. I don't think that's going to happen. On E, TRAPPIST-E, the planet in the habitable zone. But I'm going to be able to, I think, to be able to say, if it had an atmosphere, what is in it, and whether there are some biomolecules in it, and we will be moving up this scale. that means then we're also focusing on constructing instruments or the next set of measurements that we can make that will move us up this scale. And so in terms of like finding a needle in a haystack, which is sort of like, all the planets that are out there, and there's more planets than there are stars, we actually then are looking for that needle. We're looking for that other planet that has life. It's out there somewhere. But we've done a number of things to help do that. The needle is over in this part of the haystack. It's in the habitable zone. The needle is sharp, and you might have scratched yourself, or you stick your hand in there. Okay, that gives us now an even closer area. We now know that perhaps we'll take a magnet and go in there and find the needle in another way. So now we have not only a process and how we find this information, but we're confident in each one of these steps that we're moving towards me in sometime in the future, or Aaron or some other one of our scientists on that's working in this area, to come on Clubhouse and say, we got it, we know it for sure, and this is how we know, and this is what we know, and there is life on this exoplanet. Okay, so it's all part of the scientific process, and it's going to take a while, and it's important to bring everyone along on that journey so you understand how we're doing it. But we're making fabulous progress. Okay, thank you.
Yeah, thanks, Jim. That's very exciting to know. So thanks for sharing today with us. So we all know what's going on here on the space journey. So we still have some time. I will pass mic to Abyss. If you have any questions, please go ahead.
Thank you, Sierra. Thank you, Jim. I've been following your work for quite some time, and it's an honor having you here and explaining exoplanets to us. I do have a couple of questions. The first one being that you mentioned that you have now amassed about like 5,000 exoplanets. That's like Kepler and TESS combined. I'm just wondering, like, if that actually has improved your sort of like your Bayesian likelihood to essentially determine which sequence stars on the Hertzsprung-Russell, the HR scale, are likely to harbor exoplanets, or at least like have exoplanets in a stable order. That's my first question. The other one is, we recently found out that the Proxima Centauri system, even though like I believe it's a binary system, does have a planet in a habitable zone. I'm just wondering, like, if you have, if there's like a stable binary system, knowing that there is a possibility that planets can actually exist in at least like an habitable zone, how likely are you to essentially focus the James Webb telescope into looking into the binary stars as opposed to like single stars with multiple planets? So these are my two questions. Thank you.
Okay, so the first one is really an excellent question, in that there are different types of stars. Our star is what we call a G star. The TRAPPIST star is an M star, and it's colder than our G star. Still a hot star, still 2,500 degrees or 2,500 Kelvin on its surface. And all these planets are closer to these stars, and that makes it a pretty rough environment, because they're bathed in the winds of that star. They're being hammered by coronal mass ejections and flares. And so that's a problem. We are lucky that we have a G star, because that means we're far enough away. The habitable zone is far enough away that it's not as rough on our atmosphere, the solar wind, as it is the TRAPPIST wind hitting these exoplanets. So that means they need a magnetic field to help protect them. If they don't have a magnetic field, then it's doubtful they're going to be habitable. That's my opinion, my personal opinion. it'll be just too hard on the atmosphere of the planet for too long a period. It'll be more Mars-like. You know, Mars started out as a habitable planet with an ocean. It lost its magnetic field, and indeed, the solar wind's just been doing nothing but stripping the heck out of the atmosphere. Venus, it lost its magnetic field. The only difference is Venus is still very volcanically active and is just kicking out the atmosphere like crazy. And even though the solar wind is pouring, just stripping the heck out of the atmosphere, Venus is replacing it, unlike Mars, where it doesn't have any active volcanoes. So that's the difference between those two. So indeed, star types are very important. Now, when you look at star types, you find that 75% of all stars are like these M dwarfs, okay? They're like the TRAPPIST-1. And so that means we really need to study this system very carefully, because if life, the probability of life existing on these type of stars must be greater than some of these other stars, because there are so many of these M-type stars. Once again, 75% of the stars in our galaxy are these M-type stars, which is what TRAPPIST is like. And that's why it's really important to look at them. And I think that answers your first question. What was your second one? I'm so sorry.
Oh, yeah, you're good. That's actually an excellent answer. So my second question was, do you expand the sort of like the search space, if you will, to looking into binary stars as opposed to like single stars, knowing that
Yeah, right.
Proxima Centauri has like
Yeah, right.
stable.
Yeah.
Yeah.
Yeah, so Proxima Centauri is really fabulous. We're going to look at it with Webb, no question about it. You know, are there planets out there like Tatooine with 2 stars? And the answer is yeah, there are. We found several of them. And so those are really exotic. Those are really fun to look at and model and try to figure out where the planet needs to be, what the habitable zone of that planet would be, to be able to then determine which of these double stars with planets in it would be what we would want to look at. So a lot of work needs to be done yet in that area, but they're out there. Thank you.
Great questions. So pass the mic to Cecile.
Yeah, thank you so much, Jim, for being with us here in Quantum Photonics. Yeah, we hope this will not be the last one. We really want you to be our guests, our guest here in Quantum Photonics again, knowing that there's not so much time. So I would just like to ask, as of now, what are what is the steps? What is the roadmap of NASA towards looking at this extraterrestrial life?
So we're on it. You know, we're doing it in our solar system. The Planetary Science Division is working hard on a series of things. Right now at Mars, we have samples we're creating. We're boring rock, and we're going to bring the rock back. Here on Earth, our rock record is rich in ancient life. There are 5,700 minerals on Earth, and about 350 of them can only be made with life. Dead life makes these minerals, along with other material, that makes them unique. And so by bringing back rocks from Mars, we're going to really interrogate them and see if indeed in the past Mars had life on it. So we're doing a variety of things in that area in our own solar system, in addition to a whole series of telescopes that are being discussed and thought about as to follow on JWST. So we're going to have bigger telescopes than JWST. Some may be on the moon. We're actually talking right now about maybe in 50 years we'll have a huge telescope in a permanently shadowed crater in the south pole of the moon that is looking at not only exoplanets, but maybe the continents of an exoplanet or their clouds. some really fantastic things as big next steps. So all kinds of things are happening in those areas. Thank you.
Yeah, thank you very much.
Yes, thanks Cecil for the great question, and thanks Jim for the roadmap readout. So I guess we have the last question, which is our lucky fan Frank. Yeah, so go ahead.
Oh, I'm so honored to have the opportunity. Yeah. So thank you again. For your wonderful sharing. I mean, space is always my fascination. I'm just going to ask a little more a detailed question regarding the spectroscopy that a few that mentioning that in your talk, in your speech earlier, that I'm aware that the JWST probably have an open or have a plan for sharing the those data, and you mentioned that you're probably the priority will be the planet of the system you mentioned. The you mentioned that I hear you mentioned that it's challenging to it's a new challenge to look at the atmosphere when the planet going behind about transit to behind the is so is that because you wanted to see the reflect I mean instead of a transmission absorption, and you wanted yeah, so that's one of why do you want to
Yeah,
that
yeah, no,
particular interest?
you're right. You're right on it, and that is the light from the sun hits the planet in full view, and that light is reflected, but it's also absorbed by the atmosphere and re-emitted. In other words, the atmosphere processes the light from that star. And if we can just get to the right position that just before an eclipse happens, in other words, just before the sun passes between us and the planet, actually looking at the disk of the planet fully lit, okay? And it's that fully lit part of the planet that allows us to get that spectra. And that's called an emission spectra, unlike the absorption spectrum, which occurs during the transmission. So those two spectra are different, but each one tells us what's in the atmosphere. One, it tells us there is an atmosphere or isn't, and then two, based on the emissions that are occurring or the absorption that is occurring in those two techniques, what the elements are, whether they're water or carbon dioxide or methane or, so that is indeed the process. And JWST is capable to do that on so many ways. One thing you touched on that I want to elaborate on is the data and the access to the data. JWST is one of the first modes of operation that it's going to do is take a whole slew of data and stick it in the archive for everyone to get access to. There'll be no proprietary periods for this initial set of data that it's going to make. For instance, in the solar system, there's a slew of measurements that are going to be made from Titan to Europa to Mars. And as soon as that data is taken, it's going to be stuck in the archive and accessible to anyone. So it's not only scientists, it can be people that can take the data and color it, and because there'll be fabulous images, there'll be fabulous spectra, and it'll be readily available to anyone. It'll be an open archive, and that's important for many reasons, one of which is indeed that's going to help people then, scientists in particular, to work in teams and propose the next step of observations based on the observations that have been made and the success of those observations. In other words, if we think we're going to look at Mars in a certain way, and we take that data, stick it in the archive, and everyone looks at it, and it's overexposed, it's not usable or only partially usable, then we know what to do next and how to make a better set of measurements. So the only way we're going to be able to get everybody up to speed on how to use the telescope is to just hand out the data as free as we can, and let them work with it to understand what the next best steps are to make the next best set of observations. Okay? Thank you.
Thank you.
Yes, thanks, Jim, and thanks everyone for the great questions and discussion. So thanks for joining us to share your the inspiration, and thanks for being with us to explore the edge of the possibilities. So definitely, we are looking forward to see what's going on and what will happen in the next decades. About the new lives exoplanets. So yeah, thanks Jim again to guide us and shed the light here on this fascinating topic. So looking forward to the more room in the future. Yeah, I have to call a hard stop here because I know Jim has another yeah commitment. But again, thanks everyone. Thanks Jim.
Thank you so very much, Sierra. Indeed, I have another room I'm going to have committed and have for many, many months now. I think we've gone to a year where on Thursday night at this time, we talk about the latest news in NASA. So it's in the it's in the astronomy and astrophysics room for an hour. We've got three or four top stories we're going to talk about, some of the latest discoveries. Of course, please, for those that are new, that have come in, that haven't been in this room before, quantum photonics, Sierra does a fabulous job with many different subtopics. It's a wonderful, wonderful club to be part of. And of course, you want to follow the people on stage. And thanks once again for a wonderful opportunity to talk about one of my favorite subjects. Take care now.
Yeah, thanks, Jim. And yeah, if you like today's topic, feel free to join the astronomy and astrophysics club with Jim now. And I will see you guys there. And I will invite the sale. So let's do a quick countdown.
All right, great room, Sierra and Cecile. We're going to start with lucky number 5 for our countdown. Is everybody ready?
Yeah, ready?
Ready?
5,
Five,
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 5,
4,
four,
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 4,
33 and a third,
three,
two,
33 and a third.
33 and a third.
Where's my compass and protractor?
2,
two.
two.
2. So Sierra, Abyss, Cecile, you're all number 1. Call it out.
Lucky
Bingo!
number
Yeah,
1.
thanks everyone, and see you in the astrophysics club if you still want to yeah continue to learn about space. And also see you soon in the quantum photonics club same time at 7 p.m.
Yeah, the next room will be about the geopolitics of semiconductors. So it's an exciting room. Join us tomorrow evening in quantum photonics. Yeah, bye for now.
Bye, everyone.
Have good dreams. Good night.